Greetings, everybody. I'd like to welcome Elizaveta Kovaleva, who is applied to join us as an associate research scientist. And she's going to be speaking to us today about zircons and other cool things. So I'll turn it over to you, Elizaveta. Welcome.
All right. Thank you, Mark, very much for having me here and for introduction. Today, I will tell you about a shocked zircon and how the shocked zircon can record the conditions of extreme planetary events. And this is a work which involves a lot of people, not just me. So that's why it says Kovaleva and co-authors. This is on the left-hand side. It's an electron microscopy image of this granular zircon, one of the types. And on the right-hand side is just my photograph. I was asked to say a few words about myself, my background. In 2010, I received a Master's of Science in Geochemistry and Master's of Education in Geography. And I got it from here. It's Moscow State University. It's in the top 100 universities in the world. This is obviously not the whole university. It's just a few faculties. On the lower left, it's the chemistry faculty building, and on the lower right is the physics. And I spent a lot of my introductory hours in this two buildings. And then my faculty was in geology, geography, and mathematics. Three faculties were in the main building in the center. And yeah, geology faculty is among them. And then for about a year, I was a research engineer in the Institute of Experimental Mineralogy from Russian Academy of Sciences. It's in Chernogolovka, near Moscow. And after that, after this brief position, I got a PhD position in the topic of deformation of geological materials. And that was in the University of Vienna. It took me 3 years to do my PhD. This is a new campus on Spittelau, where I was studying at the Earth Science faculty. And after that, immediately, I moved to South Africa, and I was a postdoctoral researcher there for 4 years. And later on, I served as a senior lecturer in mineralogy and plate tectonics, and that was in University of the Free State. You can see I moved back to posh buildings. And after that, in the very beginning of 2021, I got a lecturing position in structural geology, geotectonics, and field mapping. That is in University of the Western Cape in Cape Town, where I'm currently lecturing at this very moment. So this is the campus from aerial photograph of the campus. And just a few kind of milestones in my career, which are maybe significant in terms of like progression. One of my postdoctoral terms was sponsored by National Research Foundation of South Africa. I was a freestanding postdoctoral fellow between 2017 and 2018. I was also an invited lecturer at the University of Lille in France. Both of these positions, why I put it here, it's rather competitive positions, especially the postdoctoral fellowship for a foreigner. So it's an achievement. And I'm also rated by National Research Foundation. We have a scientific rating system, and I'm rated in the Y category, which stands for young. For another couple of years, I will hold that kind of an honor. And then later, I was also, I became a scholar of Russian Science Foundation. We had a large team, and I was a PI. This project was designed to run for 3 years. Unfortunately, it was terminated prematurely because of a political situation that we all know about. And at the same time, I also became an Alexander von Humboldt Fellow in the category of experienced researchers. And surprisingly, that I was able to complete. So for 3 years, I was spending several months of each year in JFZ Potsdam in Germany, doing research, which I'm going to actually present to you now. So this is kind of my path, very in a nutshell, very briefly. And let's now move to the fun part, the research part. I will talk about shock metamorphism. I'm sure that most of the people who will watch this talk know about it, but just to briefly explain to refresh the memory. The shock metamorphism occurs when you have a projectile, it's usually a comet or an asteroid, which are moving with hypervelocity speed with respect to the surface of a planetary body. And then it hits the surface moving at the speed between 10 and 70 kilometers per second. So 10 kilometers per second, which is written in this image, it's kind of a lower boundary for that velocity. And at the point of contact, the collision produces vapor, and then a little bit below point of contact, we observe melt, and then the zone of shock metamorphism. Those are the zones which are shaded in this image. Below the zone of shock metamorphism, we have just the zone of enhanced fracturing and brecciation. Usually the impactor is completely destroyed in this scenario. And these two zones, melt and shock metamorphism zone, represent really unique rocks. We don't see these types of rocks forming in any other processes, any other natural process, at least on the surfaces of the planets. And I'm sure like in their interiors also. And yeah, just to kind of round up, we have a hypervelocity, the collision happens, and it involves a vaporization of impactor. At this point, we have a formation of a meteorite impact crater around the point of collision. We very often observe circular geophysical anomalies, gravitational and magnetic, and we observe shock metamorphism of rocks and minerals within the target, because like the impactor itself is destroyed. And this shock metamorphism is one of the key criteria to identify impact event, impact process, because circular geophysical anomalies or some round features like crater-like features can form as a result of other processes. But if we have shock metamorphism, we know that that was definitely an extra kind of, when we speak about Earth, we call it like extraterrestrial process collision. And this is what I'm going to tell you about today. All my research falls under a category of shock metamorphism. Why do we care about this impact craters? I'm also sure like all of you have an idea, but just to recap briefly, first of all, impact events serve as a basis for stratigraphy and age dating. At least we use them widely for Earth, Moon, and potentially we can also use impact events for other planets. It can cause hydrothermal activity. For example, it's very common on Mars, but also on Earth in case of large impact structures like Chicxulub and even Vredefort. There is an idea that the Witwatersrand gold deposits, the gold was mobilized because of the hydrothermal activity, post-impact hydrothermal activity in Vredefort. It can also cause volcanic activity, like we see in the case of the Moon. And specifically for Earth, we have enormous economic significance of impactites. For example, in Sudbury, we mine for nickel, and nickel is hosted directly by the impact melt bodies. In Vredefort, we have gold, iron in ejecta, and then helium in the core of the crater. probably for us as humans, we also are very worried about like our survival and evolution of life. And of course, impact events affect ecosystem and biosphere, such as the most probably striking example is the Chicxulub, which killed the dinosaurs and caused ultimately the mass extinction. And probably because of it, humans had a chance to become dominant. Now, I am specifically looking at a mineral called zircon. It's zirconium silicate. And it is also quite a significant mineral because it's a very common accessory mineral for many types of rocks. We know it from Earth, from the Moon, from the Mars, from various meteorites. So it must be common in rocky bodies. It is quite robust and refractory, so it is quite difficult to recrystallize or melt or deform these minerals, which means like other minerals will melt and zircon will remain under certain conditions. It is very widely used for isotopic dating of magmatic metamorphic events, also meteorite impacts on Earth and on the Moon. I'm sure it's possible for other planetary bodies as well, especially as we will bring back samples from other bodies, rocky bodies. It also can be used for geochemical characterization of its forming environment. It contains a lot of trace elements which can signal about various conditions. As one example is titanium and zircon thermometer. By measuring titanium content in zircon, we can identify the temperature of zircon crystallization. And I need to mention that zircon usually occurs in nature as a single crystal. It has tetragonal symmetry. And very rarely it forms growth twins or some kind of intergrowth, and only in very, very viscous melts. Usually it's a single crystal, well shaped with nice crystal faces. On the right, you can see the crystal. I don't know if there's this panel which covers for me part of my slide, but I hope you can see the slide. On the right-hand side, there's a cathodoluminescence image of zircon. Cross-section, you can see that it has a nice tetragonal symmetry and it has growth zoning, which shows different environments in which it grew. First kind of news about shocked zircon came from Sudbury in 1992. That's the very first publication. I mentioned to you that zircon is a single crystal, and these two images show surfaces of those of the crystals that were found in Sudbury. And on the left, you can see the lines on the surface looking like cleavage, or kind of looking like planar deformation features in quartz, except that zircon does not have cleavage. So they were called planar deformation features PDFs because they didn't know what to call them, really, what they were. And on the right, you can see that the surface of the grain is covered by this little kind of granules, and they call them strawberry zircon. It looks like strawberry seeds. And nobody knew why it forms or how, but it was clearly associated with shock deformation. A year later, this very similar stuff was found at the KT boundary. That's the ejecta layer associated with Chicxulub impact, 66 million years old. And again, you can see like when you zoom out, you see a nice kind of comparatively large single crystal. But when you zoom into the surface on the far right, that's a picture of the surface. You can see that it is composed of small grains. And again, it was not known why or how. And finally, a few years later, it was also found in Fredeford. It was a separate, heavy mineral separate from the impact melt. And again, you can see like a single crystal. Okay, it is maybe broken and the faces are not that very well developed, but you can still see that it is a crystal. But when you zoom in on the surface, again, this tiny little grains or granules. And those were the very first reports of the shocked zircon. Again, I want to emphasize, we didn't know what they were, how they formed. Today, there are multiple shock metamorphic features known in zircon. They're better defined. And the first one is radite inclusions. Those are high pressure polymorphs. So it's a mineral with the same composition, but a different crystal structure. And hence it is denser. And it only forms at very high pressures, which are not normally achieved in Earth crust. On the right, you can see a transmission electron microscopy image of such zircon matrix containing radite, those bright lines, and like kind of a network of very fine lines. This is radite in the darker matrix of zircon. So it used to be a single zircon grain. It was shocked, and along certain planes, you can see that it transformed into a different mineral. We also observe shock polysynthetic microtwins, just like we have polysynthetic microtwins in plagioclase, for example, except that for plagioclase, they are growth twins, and for zircon, they only occur in under shock conditions. We also can observe planar fractures. I mentioned that zircon does not have cleavage, so it's quite unusual for it. Quite often we see zircon cores surrounded by rims of padellite crystals within a silica matrix. That indicates decomposition of incongruent melting of zircon, probably under high pressure and high temperature. And we also have various granular textures, and I'm going to tell about these granular textures today because for me they're the most interesting. And why am I telling you all of these different features? Because each particular feature is associated with a particular pressure, temperature, cooling, and differential stress conditions. So looking at each individual feature in the zircon, you can actually identify what kind of conditions was it subjected to. And sometimes, like all the other minerals, are completely recrystallized or molten or brecciated. So zircon very often is the only one retaining this information. So I went to two distant impact craters. Oh, obviously I've been at more than two, but I studied a lot of samples from these two craters. One is in polar Russia. That was in the frames of my Russian Science Foundation project, which was closed prematurely. We planned to visit more distant impact craters like Polygranular. Unfortunately, it didn't happen, but at least we managed to get to one crater. And then the second crater is Araguainha in Brazil, in kind of an Amazon jungle. Both of them are comparatively large. So the one is 65, another is 40 kilometers approximately because of the very complicated and eroded terrain. You can see the digital elevation images. They're not very pronounced. So the original size is really hard to identify. So those are estimates. And they're both relatively young. They're not like Fredefort, which I used to work with, which is like 2 billion years old. They are, for me, it's young. And the red diamonds show collection of samples. And Araguainha is a central uplift, and for Kara is more like a breccia infill, like a crater infill deposits. This is a trip in Araguainha I took in 2019. It was in the frames of LMI conference in Brasilia, and it was organized by the conference organizers, which was very nice. We saw a lot of nice landscape and collected samples. And then to go to Kara, it was a little bit more difficult. We had to take this vehicle, which is basically like a tank with a cannon taken off. and ride on it for about 1 day. And then we were moving on pack rafts along the river all the way to the river mouth in the Arctic Sea. So yeah, we had to endure like mosquitoes, and it was a little bit more challenging trip than the one to Brazil, although probably to get there was about the same time. So like 3 days, 4 days just to get to the place. And when I studied samples from various impactites from those structures, I focused on the zircon, and here's the high contrast secondary electron microscopy images of various types of granular zircon from these 2 different structures. I looked at probably hundreds, but here I put just a few to get a flavor of what I had to deal with. All of these are granular zircons, and you can see that they're very, I didn't put the scales, but they're also slightly different size. Some of them have very tiny granules, which you don't even see from this scale. Others have quite large granules, which you can actually see. Some have very sharp boundaries, others have fuzzy boundaries. Some have, apologies, some have wars, other quite dense. A lot of them have inclusions of bright material, like the one in the middle row. Second from the left, it has like bright inclusions, and then the top row, second from the left, also has like flame-like inclusions, and those are different mineral phases included in the zircon. Some of them have preserved initial growth zoning, like the 2 in the top row. The second and third, they have this growth zones, which are only partially crystallized, other don't have any growth zones at all preserved. And when I looked at them, I realized, no, there have to be very different mechanisms to form such a variety of textures. And but obviously from this scale, it was very difficult to tell what was going on. So we had to move 1 step down, like higher scale, higher magnification, and we had to cut transmission electron microscopy foils, focused ion beam foils for transmission electron microscopy, and look at those grains in much more detail. And after like several years probably of looking at those textures, we at least identified 5 very distinct types, and I'm sure there will be more, but the 5 that we managed to understand. And the first one, I call it type 1. There's no significance in this number 1, 2, 3, 4. It's just for convenience to refer to them. So type 1 is a zircon after radite, or a high pressure type. So I will jump to interpretation, and I will kind of attach interpretation to each type immediately, not to get you confused. This is an example from car impact structure, and you can see quite a small grain. It's probably like a fragment of a grain, and it has something inside of it that has bright and dark lines, and I thought it looked interesting, so we cut it a fib foil. And this is an image of the foil at the top right, and you can see that this brighter material is indeed radite, and the slightly darker granular material is zircon. So what happened to it? It was a single grain of zircon. It was shocked, transformed to radite. It's a high pressure polymorph of zircon, and then under certain when the pressure was released, and maybe it was a little bit heated, so the radite, which is like less stable at ambient conditions, started to revert back to zircon. But instead of a single crystal, it produced a polygranular texture. Those you can see that the black frame on the top right image shows the zoomed in area, and that area is enlarged at the lower right. You can see that it's kind of wedges of zircon in between this radite with high density of defects. Those like kind of fine lines inside the radite matrix, those are defects, probably because of the higher density of this mineral. And how do I know for sure that it's zircon and radite because they have the same composition? Well, we did spectroscopy. In this case, that's EELS spectroscopy, which allowed us to do phase mapping. And this is that area mapped, the one at the lower right. This is the same area. So the green is zircon and the red is radite. And you can see that zircon, the green, it is full of, this upper part is full of fragments of radite. So it's a kind of remains of this back reaction, the phase transition reaction. That's how we can identify the direction of this reaction, that the radite is converting into zircon, leaving behind the small irregularly shaped fragments. This is just a zoomed in, even more zoomed in area on one of those fragments. In A, you don't see anything. But in B, C, and D, this is a spectral imaging, and you can see the red is radite and green is zircon, and this kind of half moon shaped of, I don't know what kind of shape it is enclosed in green zircon. And in E and F, that's an enlarged high resolution TM images, and you can see crystal lattices of zircon and radite, which are very different from each other. So you can really see its different phases with quite a sharp contact with each other. Some more pretty images. This is the diffraction contrast images of the same. And on top, I just put an explanation of what happened. Zircon was subjected to high pressure. For shock pressures, it must be about 30 gigapascal. It was converted to radite, which is a high pressure polymorph. And when the radite pressure got released and got heated, in experiments, they heated to get zircon again, they had to heat it to 1200 degrees. So I'm just putting this experimental data. It reverted back to zircon, and this granules represent this kind of entire history of extreme conditions. This was described in Rochechouart impact structure, also in France. And here you can actually see the whole sequence. If you look at the panel panel C, so zircon is green and radite is red. So it was a single grain of zircon. It was partially transferred to radite due to shock. And then on the far right side of it, that little granular rim, radite started to revert back to zircon, but instead of single crystal, it's now composed of very fine granules, and that fragment enlarged is represented at the far right column, G, H, and I. And you can see again relics of this pink radite inside of this granular zircon mass. So it is not unique like to Clara, it's also known from other impact structures. Yeah, interpretations was more or less the same as ours. In this case, I promised I will stop and I will ask if there's any questions so far.
Yes, I've a question. Not being a hard rock person, but these zircons they're terrestrial material that gets shocked by the impact. Is that correct?
Yes. In this case, it is terrestrial material, which was sitting in the crust happily. Was a single crystal, nicely shaped, and then it got hit by meteorite, and this is what happens to it after that.
Do the meteorite, do the impacts ever form zircons? I mean, created from whatever they're made out of. I have to look back at the formula, but
yes.
Yeah. So I was just wondering if zircons are formed by impacts, or is it, or do you only see them as pre-existing terrestrial material that gets shocked by the impacts?
Well, technically, what I'm showing you is the kind of new zircon. It's newly crystallized, created by impact. The material was already there, but it's not the same crystal. It got molten or decomposed or phase transition. So when we look at this granular or neoblastic textures, I would say they are new. And if you date them using uranium lead or thorium, uranium thorium lead isotopic systems, they will give you age of the impact. That means it's the new.
Yeah.
They can also grow in impact melt, completely like new. But honestly, I haven't seen those samples, but I know other people found them. When you have large, like a melt sheet, and then from this melt sheet, you crystallize completely new rock, and the zircon crystallizes as a part of the new assemblage. So that is also possible.
Thank you.
I hope
Elizaveta, could I ask one question real fast?
Yes,
It's
please.
really fascinating. I've not kept up with the literature. Has a similar study or a comparable studies been done with lunar samples? There's a whole suite of lunar breccia classes of different impact strength processing. I'd be curious if someone is working on this with any lunar material.
Yes, work has been done, and even by my team. So I will show you a picture as well. In this type, in type 2, we found those on the moon from Apollo 16. We worked with 15 and 16. And other people found those as well. So definitely. And
Great, thank
actually,
you.
like, yeah, one of the grains were surprising, well, not surprisingly, but it was amazing. They were actually younger than the other crystals. So that means they did recrystallize during the impact. So, anybody else? Okay, then I will just continue. So the next type was formed as a result of incongruent melting and recrystallization. So when the zircon is heated, it is melting, but it's not a bulk melt with the same composition, but instead it forms two melts. It's like most of the rocks, when you melt them, it will not be just a homogeneous composition equivalent to that same original rock. It will have a different composition. And in zircon, you have zirconium oxide and silica oxide. So basically your like material which forms quartz, and then the material which forms zirconia, like you know it from probably jewelry. It's yeah, zirconia or zirconium oxide. In this case, you can see that these granules are not densely packed, they're disjointed. There are gaps in between them, and inside they have these bright inclusions. This is zirconium oxide, and in between the granules, this is silica, which are remaining from that back reaction. So basically zircon decomposes into two, and then it reacts again to form, instead of one single crystal, then you have many small crystals, like clearly visible from this picture on the left, and on the right is just a kind of closed up image. I think it's a FIB4 image. The first example, this one is from Kara impact structure, and the second one is from Araguainha, and this is like the most common type. I've seen it in a lot of environments. This is also granular texture. Here it is zoomed in, and you can see this arrows point on very tiny inclusions of, again, scale on this lower right image is 100 nanometers. So these inclusions are like 10 nanometer, 15 nanometer in size. The bright are zirconium oxide, and the darker ones are silica. So this is a product of this decomposition reaction. You can also see that this newly formed granules have very nice crystal faces. Like in this zoomed in image on the right, the brighter crystals are zircon, and then they have this darker material in between, which is silica oxide remaining from the back reaction. And you can see like straight lines as boundaries for these crystals that are crystal faces. This can only form from melt. You cannot form it from like phase transition, for example. And this like speckles inside, those are inclusions of the product of decomposition and material which built this actually new crystals back again. To answer your question about lunar zircon, we found this in a poem. This is Fib foil in A. This paper is published actually. And you can see that the large zircon granules have interstitial space filled with silica oxide, and then bright inclusions are badellite, which is a zirconium oxide. And in B, this is the same area. It's just a little bit enlarged, and it is in diffraction contrast to show that there's also like some amorphization, maybe related to later shock events. So lunar zircons are more difficult to study because they experience multiple shock episodes. On Earth, if you find some impacted material, it usually was shocked only once. It was also described by other authors, but they call it Frigon, former radite and granular neoblastic zircon. Difficult story, but they think it was reverted from radite. But this is not possible because you can see inclusions of zirconium oxide, and they even report it themselves. And then they have growth zoning, which can only form from melt. And you can see how dispersed this aggregate is. Pole figures just show the orientations of these grains. Every color shows different orientation. So yeah, it was a lot of descriptions of this particular type in literature, but some authors like have different interpretation. I disagree, but yeah, we agree. I can't really tell about their particular sample, but my samples will which look very similar. I give them different interpretation. And this is a classical kind of melting scenario where you have a zircon, you heat it to about 2000 degrees. It melts into zirconium oxide and silica oxide. And if you heat it even more, it becomes bulk melt. If you look at the phase diagram, zircon will be in the middle between zirconium oxide and silica oxide. And you can see that if you start heating it, first you will have zirconium oxide, silica oxide, right about like 2100 to 2600. Then you, at some point, you have two liquids. So first, zirconium oxide will be solid, and it will be surrounded by liquid silica, and then there will be two liquids which are immiscible, that little kind of a mushroom shape, which says two liquids. It's an immiscibility gap, and if you heat even further, if you go even up, you will have bulk melt, which is equal in composition to zircon. And then when you cool it down, it goes back to zircon. So on the y-axis, you just have temperature. And this has been modeled a lot of times in laboratories, so this is very common. And I see the same reaction of decomposition a lot in other materials. I'm just going to touch a little bit of my other projects. This is a NASA Ames shock experiment. They had quartz sand, which they hit with a projectile. And in the sand were little crystals of zircon. And this is what happened. This bright material is zirconium oxide enclosed in silica. So zircon completely was molten, and you can see it's an emulsion. Similar process happens when you mix water with oil, and you shake it, and the little bubbles of oil will mix with water, and this is what happens in this case. So zircon was molten into two different liquids. And we also found the same in natural fulgurite. This is from the York County. Fulgurite, it's a product of a lightning strike, and you can see the core of zircon, this kind of a grayish material in the middle of this aggregates, and the bright, nice kind of maze-like rims. This is zirconium oxide, which was produced from heating that zircon by a lightning. So this is a very, very common process, and we also saw it in Libyan desert glass as well. This is some TM images. I'm specifically want you to look at the image on the right. This is the zirconium oxide in the middle, and it is sitting in silica glass. And in between them, the silica glass is kind of light gray because it's diffraction contrast. And in the middle, there is a rim of zircon. So it's a newly growing zircon. The two react. When they cool down, they react and they form zircon again. And on the left, you can see the product of that. It is already a very dense network of zircon crystals with just only inclusions left from this zirconium oxide and silica oxide. Just to summarize this, I summarized it on top. Zircon was heated, it was decomposed. You can have either two liquids or a bulk melt. And then when it cools down, you have new zircon, but instead of one crystal, you have like very many small ones. And this is another type. Is there any questions about this? I hope I'm not talking too fast.
All good.
Okay. We also found the mixture of the first two types. Oh no, sorry. I'm too early for this. This is type 3. This is recrystallization of damaged material. This is an example of this such grain from Araguainha impact structure in Brazil. And you can see that there's a quite large new granules growing on the right. And on the left, you can see a preserved initial zonation of this crystal. But this dark and very porous material indicates that it's amorphous. In this case, it was amorphous because of radiation damage. So when zircon grows, it captures uranium and thorium, and then those are very radioactive elements. They start decomposing, decaying, sorry, and the radioactive particles destroy the surrounding crystal lattices, and they become damaged. And sometimes they can be like completely almost completely amorphous. And when you have such material, in this two images on the right, the metamorphic material is dark gray, and it has these pores. It's easier to recrystallize when you heat it to about 900 degrees, which is achieved in the impact. You can have new, clear, bright crystals growing. This is TM foil, and of the same process, you can see the crystalline grains in these two images. They are on the left, and they're clear and nice, and they have these curved boundaries, which indicate this grain boundary migration in solid state. And this darker material is amorphous, but it can also be a shock amorphization. But in this example, which I'm showing, this is a radiation damage. And this was found in several impact structures. And it is believed that when this amorphous material is heated at about 900 degrees, you have this nice new neoblasts, and they're usually larger than the previous two types. These are two examples, one from Redford and one from Sudbury. They were dated and they represented the age of the impact event, which confirms that they formed as a result. And in the example on the right from Sudbury, you can see like this large grain, something is in B, it's like a big mess, not really visible what's going on inside, but these little boxes, they zoom in on certain areas, and then you can see in these boxes nicely shaped, zoned crystals, which are growing inside this initial crystal, which probably was shock damaged. And then soon after this damage, they were heated and new crystals grew, and that's why they were able to date them to the age of Sudbury. And we found a mixture of the types 2 and 3, where we have this grain have large granules sitting in some kind of porous matrix. And I thought, what is going on here? So we made a FIB foil, and we see that this large, clear grains with curved boundaries sitting in a ground mass of smaller grains, which have inclusions of zirconium oxide, which tells me that this grain had a long history of recrystallization, so it was decomposed, back reacted, and then recrystallized again. And probably if we date this grain, we will get the age of the impact structure. So this is, I think, also from Araguainha impact structure. We have some, I'm going to skip the other types because I think we are running out of time. This is just high differential stress, and this is actually a single crystal, but it is composed of subgrains, which are like not quite new grains, but disoriented areas, domains of this initial crystal, which have very interesting fractile kind of texture, where a large one is surrounded by smaller ones with the same shape. This is the same grain, but in a different imaging mode. The bright lines represent subgrain boundaries. And this is the diffraction image shows that it is a single crystal, which was subjected to prolonged stress. And you need some kind of high differential stress to achieve this. And it's not usually looking like this in under normal tectonic conditions. And then the last type we found, it's like a spherulite, and I don't know honestly how it formed. My suggestion is that it's probably bulk melting. So when it was a homogeneous melt of zircon, and then it was rapidly cooled down to kind of form this snowflake shape or a spherulite. It's more like rather a ball than a snowflake. We did a Raman spectroscopy, which was just showing that it's a very damaged structure. And this is how it looks like under transmission electron microscopy. Single crystal, long, elongated, alternating subgrains with approximately same orientation. How it forms, yeah, I can only suggest bulk melting and very rapid quenching. Similar texture was found in Chesapeake Bay. They called it dendritic texture, and they interpret it as a solid state transition. But I don't quite see how the dendrites can grow in solid. But obviously, this is an open question, like what is going on? Maybe it's something else in their case. But looks quite similar to what I've seen. And just a take-home message, every single of these different types represent a different pressure, temperature, and time path. For example, type 1, you have a very high peak of pressure, and then pressure released, and then you have a slight cooling, and then the radite goes back to zircon. Type 2, you have smaller pressure but higher temperature, which is causing melting, and then recrystallization back again. And so each of this show a slightly different PT and time path. And I think this is just my main message here, because it's quite complicated textures. And if you remember this, I think I did my job. This is all of my co-authors, which were involved at different stages of the project with sample collection, sample preparation, analysis, discussions, and so on and so forth. This is quite a lot of people, and I'm sure there are more, but those are just from the top of my head. And yeah, let me stop here and ask for more questions.
Okay, thank you very much. I have a question inspired by this diagram. So when you go to a crater, an impact crater, is there a like geographical clustering of the different types of zircons melts here at different say distances from the center of the crater or whatever, depending on how things get scattered out. I'm just thinking that different material experiencing different pressures might be in different places in a systematic.
Yeah. This is a tricky question because in an impact, everything gets so mixed up that you have very often you observe these very different textures in one sample or in the same horizon. So in a very, very general terms, you probably can say that in this type of impactite, you're more expected to see this type of microstructure. In brecciated rocks, you will not see like radite, for example, in the material like under the crater. You will probably see it only in like impact melt and suevite. And so very, very generally, you can assign those textures to geographical kind of or stratigraphic levels in the crater, but they can be very much mixed together, and to the point that you will see two crystals sitting next to each other in the same fragment. One will be completely intact and one will be shocked to dust. This shock metamorphism process is very inhomogeneous, and it just very much depends on the local environment. So we can estimate peak pressures and temperatures. Okay, in this particular area, this is the peak pressure which was achieved. But we cannot really like define the boundaries because, as I said, like in one sample, you will have like completely shocked grain and then completely unshocked grain. So they experienced different deformation. But we can talk about the one which was shocked and which pressures did it achieve. And that we can identify the peak pressure. I don't know if that makes sense.
No, I was thinking of things in terms of a spherical cow, and that yeah, things are always more complicated than that. So, any other questions for Elizaveta?
Maybe one more, Elizaveta. These are awfully small grains and probably hard to analyze chemically, even with something like an ion microprobe. Has there been any systematic work of things, of the minor elements like uranium, thorium, and hafnium that you often find in zircon in these grains?
Yes, they are being dated every now and then. And the larger, if you have this larger neoblasts, they're very nicely showing you the age of the impact. And that's why I think they will be very useful when we have sample return missions and we find this neoblastic zircons. We can actually reconstruct the planetary histories or like asteroids or whatever. If I'm talking about myself personally, we did this with Araguainha, granular zircons, and we roughly got the age. We wanted to get more precise age than, because there's been some arguments, but because from Araguainha they were the granules are quite small, and I think there's a lot of like small inclusions, and you're ultimately the analysis, the seams we did seams in Stockholm, they get contaminated, and we did get a very rough kind of age of Araguainha impact event, but we didn't get like more precise than has been done before. In that case, it was a bit disappointing, but various impact structures get dated using those neoblastic zircons. And they are quite precious because I think there have been like less than a quarter of all the impact structures. I don't want to lie, I don't remember exactly, but very small, relatively small percentage were actually dated. And if we will start looking for this granular zircons, we can actually date more impact structures.
Oh, thank you. These are definitely difficult samples to work with. It's impressive. Thank you.
Thank you.
Any other questions for
maybe I want to add something. I meant to say that it's not only impact events, but other kind of planetary extreme events, like lightnings, for example. And we know there are lightning storms on other planets. So we can probably identify the presence of those atmospheric events on other planets, like surface samples.
Yeah, your evidence of the fulgurites was news to me. I had never thought about that.
Yes, but we were looking for high pressure and we didn't find the high pressure indicators in fulgurite. So they are quite high temperature rocks.
I
Yeah.
I don't know what kind of how energetic an impact has to be to you know, create these zircons, but I wonder if in other meteorite samples that there are or zircons found in other meteorite samples that may have come from earlier collisions among asteroids.
Yeah, no, definitely.
Hmm.
I think there was some study in Martian, one of the Martian's meteorites. They found a zircon with shock microtwins or something. So yeah, and we can actually tell what happened to this meteorite on the way. Because yeah, when it was ejected as a result of the impact, and then it traveled, and then when it was collected finally, yeah. So that is why this research, I think, kind of has potential for also studying extraterrestrial objects.
Great. Well, thank you very much, Elizaveta. It was a very interesting talk.